Okay, folks, we're still doing hypothesis testing. It's week 12, and we're doing the second half of chapter 9. I really want to give this enough time so it'll sink in and soak in, and you can see what's going on here. Really, what we're doing is using the same statistical principles of the confidence interval we've studied for a number of weeks now, but just putting it in a slightly different context of hypothesis testing. Problem I want to do this, I'm going to do two problems since we have two sections this week. The first is 9.59 on page 370. We have the whole food stores, excuse me, and they want to know if they've really struck gold. They claim that in years past they've been producing $800 per square foot of real estate in revenue. That's a lot compared to the national average of um, quite a bit less. When it was $400 a square foot for the competitors. They want to know if we're really doing better than that this year. Um, Better than $800 per square foot. Now, they took a sample of 10 stores. You can see I've got the data plunked in here. And they came up with an average sales per store of $846.20 per square foot. The standard deviation for that sample of 10 was $32.86 per square foot. But so we have to ask the question, is that really good enough? 846 sounds like a lot more than 800, but is that, considering the standard deviation of 32, does that really cut it? Now, the other problem is we have a sample size of only 10, so we have to ask ourselves, what are we doing here? Is this really going to work? Can we use a sample size of 10? Flip to page 386 and look at figure 9.18 on that page. This is a handy page to keep around. There's one like it in chapter 8 too. This tells you how you ought to do the analysis. We start out at the top. The first diamond says, is the value of sigma known? Do we know the standard deviation? Now, all we know really in this case is the sample standard deviation based on a lousy sample of 10 units. Not big enough, so we have to answer no there. Is the population normal? Well, we don't know that. And so the next step is the population mound-shaped at least? I mean, is it not very skewed? Does it have just one peak? Well, I did a little histogram here. I won't bother you with doing it. Just use Excel's histogram function. Let it choose the bins, and hey, it looks kind of, if you squint at it, not too bad. Okay, so we'll say yeah to that one. Now, what if we said no? No, it is mound-shaped, or it isn't mound-shaped, or it has two peaks. Well, then the next question is, n large enough? Is it greater than or equal to 30? If we answer no to that one because we only have 10, then we're out of luck. We've got to go back to the stores and get some more sample data. But we'll say yes. So that is telling us, however, we have to use the t-distribution, which is not at all surprising since that happens to be the section of the book we're studying right now. So you could have guessed that, I suppose. Okay, that's what we know. Now we need to come up and use it. The book wants us to use the p-value to test the H0 for various alphas. Now, as you know, we could do this one of two ways. We could say, all right, I'm going to take the sample data, the x bar and the s that we've got, and I'll come up with a z-value that corresponds to. And then for each of the alpha values I'm interested in, and the book tells us it wants us to compare it at what, 0.10, 0.05, and 0.01, 10, 5, and 1% confidence or level of significance. So I could do that. I could calculate the corresponding z-value for each of those three levels of significance. But let's do it the other way around. Let's calculate a p-value associated with our test statistic. And then all we have to do is compare that to 0.1, 0.05, and 0.01. So we need a handy-dandy formula. I just happen to have one lurking around here. Let me pull it out. And it says that the t, I should call this t instead of z, is equal to x bar minus mu 0. That's the average value from our sample less the mu 0, which is the value that we're shooting for, the 800. Divide that by the s. We don't know sigma, so we're using s, which is divided by the square root of n being 10. So let's plump those numbers in and see what our t-statistic becomes. This is our test statistic, equals the quantity I'm just going to click on them now. The mean X bar is that number minus mu0, which is that number. Close that parentheses, divide that by another parentheses. The S value, which is 32, change, which we're going to divide by the SQRT, square root of 10. Got to close the other parentheses, and voila, I get 4.45. Look in the book, they actually gave us this number. I didn't have to go to this trouble. 4.45 is what, is it Megastats? Who believes them? Minitab. We do it the old-fashioned way, right? Okay, that's our t value. Now, what we have to do is find out what p value is, so corresponds to that t value. Well, we can flip back to our good old table 3 on page 315, table 8.3, and we now know, and first of all, need to know the number of degrees of freedom. Degrees of freedom, as we know, is equal to the sample size minus 1. So sample size is 10, subtract 1, get 9. I'm going to scan my eyes across the 9 line there, the 9 row in table 8.3, and 4.45 looks to me to be somewhere about halfway, and I'm just guessing, halfway between 0.001 and 0.0005. So that would be 0.00075, right? So the p-value equals 0.00075. That's a little bit bigger than 0.0005, but not quite as big as 0.001. That should be right. You know, there's a better way to do this. We could use Excel and say, I want the t distribution of my x, it calls it x, I call it the t value, that value with 9 degrees of freedom, and I only need one tail. Remember, this is a one-tailed test here. I want to know if it's greater than. I'm not worried about anything that's less than 800. It's only if it's greater than 800. So I want one tail, and I get a p-value of 0.000806. Okay, so I was off a little bit. Hey, give me some slack, right? If you round 0.0075, it comes out to 0.0008. So that's good enough. Doesn't really matter, because look at what the what am I looking for here? Compare that to our alpha values. 0.01, 0.05, 0.10. For Pete's sake, we're way better than that. So yes, we're have. How much confidence do we really have? Well, look at the table on page 362. That tells us that we can be at the 0.001. We have extremely strong evidence that H0 is false, and we should accept H1. Whatever is better than really strongly, I guess we're really strongly believing this, because our value is better than 0.001 even. Okay, so the people at Whole Foods can feel very comfortable that they're beating their own average. Whatever they're doing this year, better keep on doing it next year. Next, I'm going to do a proportion value problem, and I'll post that as a separate video.